Hello and welcome to the Business Talk podcast. I am your host Deepak. Today we are excited to have the esteemed Professor Marcelo Guerra Hahn join us. Professor Marcelo is an associate professor at Lake Washington Institute of Technology with over 15 years of expertise in software development and data analysis. Professor Marcelo is deeply passionate about leveraging data to enhance decision-making processes. His impressive career includes significant contribution to Tableau and Microsoft, where he worked on diverse teams including C Sharp, C++, and Azure. In this episode, Professor Marcelo will dwell into his research topic on the evolution of algorithms from classic to cutting-edge techniques. He will take us through the fascinating journey of algorithm development, highlighting the progression from fundamental concepts to the most innovative techniques in the field. Professor Marcelo, we are truly honored and delighted to have you on the podcast.
Thank you. It's a pleasure to be here. Thanks for setting this up and having us together.
Professor Marcelo, could you provide a short evolution of the use of computers?
Yeah, absolutely. So this is a very fascinating topic. And if you think of it, I wasn't born back then, but you may remember from some of the movies, the first idea of a computer actually came from a calculator. And what people started doing is the calculator was the basic thing that we could implement an algorithm and make it do something. And people started adding more functionality to that. And that gave light to the first machines that you could put some input on them and get some interesting output out of that. Now, those machines were really expensive and pretty hard to build. So the mechanic there was you had the machine and you had to go and use it. So big universities, big companies own these machines and they will use it. Sometimes they will rent it and you would be able to go there and get your computation done in the big machine. After that, we were able to start connecting terminals to those big machines. And that's when the idea of the mainframe came, which is instead of having to go to the machine, now you can connect to that through the terminal, even though they were still physically connected to the machine. It's not like today there was a cable somewhere that was doing this. But now we had more people being able to do computation because you could access the mainframe from your desk or wherever you were. And then the next revolution happened when the personal computer appeared. So this idea that instead of having to be close to the mainframe or have to be in the terminal that is in the mainframe, now you could actually have a computer in your house. And this one, I did not see as much because I wasn't born yet by this point, but I can already imagine how impressive it was to be able to just take this box, put it in your desk and get some stuff done. Now, for people who are seeing computers today, what these computers did in the past seems pretty rudimentary and quite simple, but the idea to have that machine, which was pretty big, doing this was very impressive. And that's what started the revolution that led to us now talking and me being able to do this from my laptop instead of having to travel your way or do the interview using more complicated methods. The next thing that happened after that is that we got the internet. So now, instead of me in my machine, in my house, doing things, I could be doing that while interacting with other people on the internet, while getting information from the internet and while being able to go back and forth. This one I did live through, so this happened when I was fairly young, and you could definitely tell the difference, right? I went from my computer was mostly for doing home things and spreadsheets and documents and playing games to being able to now get anything I wanted from the internet, interact with people, talk to my friends in other countries. So it was a massive revolution to be able to connect computers to each other at this scale. The next thing that appeared is going to be the cloud. So the cloud is a little ironic because it kind of brings us back to the mainframe in a way. So now, instead of me having to do all the computation in my house, I can send back the computation, again, mainframe style, to the cloud, and now the cloud will do it for me. So now I have a supercomputer in my house that can do a lot of things. And even if that is not sufficient, I can rent some time in the cloud, or I can send some stuff to happen in the cloud and make it faster. This simplified a lot of things because in the in the days of the personal computer, if I wanted to install something, I had to go to the store and buy something, or I had to download it from the internet and do that. And so the computer use was fairly limited to people who knew how to do these things. And most of us using computers had some idea of what an operating system was and all those pieces. But once the cloud became a thing, now anybody goes to a website and all these things is hidden, and they can just play around with that. And then the last step, which is not that old, it has some 10, 15 years, is when AI and IoT appeared. So we'll talk about AI in a minute, but the idea is that we have a new set of algorithms and ideas that can make our life much simpler. And we also have every device connected. So in my house, almost everything is connected somehow to the internet or the network. So I can tell when my door is open, when my lights are up, and all that stuff. So that is part of what we call the Internet of Things, which is to bring not only your personal computer to the internet, but everything else. And so your refrigerator is on the internet, your heating system is there, and that allows you to do a lot of very interesting optimizations and ideas. And that is where we are today. So it's very exciting to be living in this time where so many awesome things are happening at the same time.
Very insightful. Thank you, Professor Marcelo, for taking a journey to the next era. Professor, can define what you consider the foundational concepts of algorithms?
Yeah, absolutely. So an algorithm is basically a set of steps that we use to solve a problem. So we've been doing algorithms for a long time. It's just that the word algorithm didn't become particularly interesting until we started using computers and we were to program the computer. And so we call the thing that we put in the computer an algorithm. Without going too far back, if you think of just when you were in school, the first algorithm I remember ever learning was the algorithm to add two numbers. And so you had this technique where you would put one number and then you would put another number below, and then you will take the last digit of the number and you will add it. If that thing was more than 9, then you had to carry over, and then you will put the thing down there. So from very young, this I learned when I was like 6 or 7, I was already learning an algorithm. It's just that the teacher wouldn't call this an algorithm. He would say, hey, just this is the mechanism to solve the problem. Now, we already had calculators back then, so you could already tell that those steps were mechanical. So even though to me, I like math, so they were fun to perform, they were not a task that was particularly needing of me, because it was just a very simple set of steps. So now you can start seeing how a machine could already start playing around with this. So when we are dealing with an algorithm, then the basic ideas is going to be, I have an input. So in my example of adding two numbers, the two numbers are the input. And then I have something that I want to get from that, the output. And in general, we want to define the output as what it is based on the inputs. So for example, I want to add the two numbers. So the output is going to be the sum of the two numbers. And so with that, we start building an algorithm. The trick is that the more complicated the algorithms get, the more likely it is that we are doing something wrong. And so when we talk about doing things right or wrong, we are talking about algorithms need to terminate. So we want to send the computer to do something, or even a person to do something, and we want them to eventually come back. So it's very important that the algorithm has some mechanism to stop. We also want the algorithm to be correct. So if I want to add two numbers, I want to see the actual sum of the two numbers in the result. And for that reason, those are two very important ideas. The algorithm needs to have input, output needs to be correct, and needs to finish. And then on top of that, because we have time as a constraint, and I cannot have the computer do something forever, or even for a long time, then we also care about what we call efficiency, which is, okay, we can add the two numbers. In one algorithm, it may take me like a minute. In the other one, it takes me a microsecond. So I will go with the microsecond. So that component is very important, and it has to do with not all algorithms are made the same way, and not all solutions to problems are equal. And it becomes then very important to try to measure the things that we just talked about. The original algorithms, like the ones that come from math, people spend a substantial amount of time trying to make them as fast and as efficient as possible. The newer algorithm is if you're like a computer programmer and you're programming your website, you don't spend weeks or months trying to make your algorithm efficient. So as more people start writing algorithms, this issue becomes more and more important. So if you go to a website or you run an app and that app is running slowly, that is likely because something is messed up with the algorithm. And again, the person who wrote that probably did not spend their career thinking about how to make it fast the way people did with math. So that plays a role there, and that's why we have to monitor those things. But so those are the main concepts. Then we want input, output, correctness, termination, and efficiency.
Very insightful. Uh, why do algorithms play such an essential part in computer science job interviews?
Because of this thing that we were just talking about, which is in computer science interviews, we're basically trying to determine if the person is going to be able to create a reasonable algorithm to solve a problem. And if the person who is interviewing doesn't have a good grasp of, well, if I put this, it's going to be slow, and if I put that, it's going to be fast, then we run a big risk that that person will write something that is not efficient enough. It doesn't have to be perfect, but it has to be efficient enough. And now think of a big company like when I was working at Microsoft, the team that creates Windows is thousands of people. So if we have thousands of people writing algorithms that are not very efficient, then the whole system is going to be very, very slow because everything that you touch is going to be slow. So you have to be very careful that even though the one feature that you implement, let's say you are implemented like file open, is not going to make the whole system too slow and it's not going to make your take hours. If that takes an extra second, and then when I say save, it takes an extra second, and when I try to correct the grammar, it takes an extra second, overall those seconds pile up. So it's very important that software engineers develop the most efficient thing they can come up with. Again, this doesn't mean they have to do like complicated math analysis or write a paper about the algorithm unless it's a crucial thing, but they have to be pretty good at creating the fastest thing they can. And so that is why it is okay to say, hey, I know a programming language, I may not know another one. Those things are very learnable. But this idea that you instinctively want to write something efficient needs to be right there. And that is why that is one of the key components of the questions that we ask during interviews.
Yeah. Can you discuss some of the most innovative algorithms?
Yes, so the most innovative algorithms are by era. So what was most innovative a long time ago, now it seems silly. And then what is very innovative now, hopefully will seem silly in like 100 years from now. But the most innovative algorithms at the beginning, as I was saying before, are all math things. So if you think of things like the Euclidean algorithms or even the math operations, back in the day, those were innovative. Today, again, we teach them to elementary school students, so they're not as innovative, but that's what we had here there. Then all the things that happened once we started having an actual machine that could process things were also very innovative in its moment. And you can think of all the algorithms from the punch card time of the machines. All those back in the day were considered very innovative. Today, the cutting edge algorithms are all the ones that have to do with AI. That is where the field is evolving. And so if tomorrow you can come up with another algorithm to train an AI that will make it better than the current ones, then that will be the most innovative. So if you think of the algorithms that train and the ideas behind training something like an LLM, that is the top innovation of this decade.
Yeah, very nice. What prompted the transition from classic algorithms to machine learning?
That's a very interesting idea because a lot of the machine learning algorithms have actually been around for a long time. The concept of something like a neural network was not invented last week. So that has been around for quite a while. The problem is that the people doing this in paper always struggle with how much it will work in hardware. So I could invent a brilliant idea that in theory will solve an interesting problem, But then I go to the machine, and the machine is not fast enough, or the machine doesn't have enough memory to do it. So the main constraint that we're seeing lifted right now is space and speed. So the first computer that I ever had was way slower than my phone right now. And all the things that I did back in the day, it took a while to play and to do, and the phone can do that much faster now. So the computers that we have as servers, well, the desktop computers are also much faster, the servers are much faster, and the storage is much cheaper. So what has happened is that has opened the door to actually implement a lot of these ideas from the past. And a lot of these algorithms that would have not been executable because the compute power and the space wasn't there, now they can be executed. We now also opens the door to invent more innovation because now we can see what happens. We can see what the results of that execution has been. So I would say it has been substantially related to the compute speed and how that has become much faster, the amount of space that we have, the amount of data that we can move around. Well, one side note here, the internet also became faster. So now I can gather data faster from multiple sources. And then, of course, actual innovation. So people are looking into algorithms and inventing new things. But the biggest driver, in my opinion, has been this ability to compute and move information much faster than we did in the past.
Yeah. How has the availability of data in recent years influenced the development of algorithms?
That has been fundamental because if you think of a machine learning algorithm, the machine learning algorithm itself is not that weird. It's not like you're writing millions of lines of code to do this. It's all about the data. So the example here would be something like chess. So in the old days, and we try to program a chess computer, we would say, hey, here are all the steps that you have to follow. So if you have this situation, do this. If you have that situation, do that, and so on. So it will be a lot of lines of code of the developer trying to predict what thing will happen. And if your king is in risk, do something. And if you are almost there with checkmate, do that. While the new approach is, instead of doing that, let's just give a computer all the chess games in the world. And let's allow the computer to do what the developer was trying to do, which is try to abstract what the dynamic of the game is. And instead of having a human do that based on their recollections and information, let's have the computer, let's throw everything at it. And now the computer can do much better because the computer can see the patterns, can see that when this situation was present on the board, this reaction caused the player to lose, this reaction caused the player to win, and we can continue to study that. But that is only doable if you can see all the games. Like if you only see, or well, a substantial amount of games. If you only see 5 or 6, there is nothing you can extrapolate from that. But if you see millions of games, hundreds of millions of games, now this is perfect. So the only way you can make these machine learning ideas work is you have to have a lot of data because the computer is still not as smart as the human. Like if I watch a number of chess games, like hundreds of them, I may be able to see the pattern. The computer is going to need much more than that to see the pattern. But if you show me a million, I won't be able to see them because I don't have enough time to see them and my brain doesn't go that fast. So if you have a lot of data, the computer will do a fantastic job. So that is why it's very important to have that data, to have people producing that data, and to have people be willing to share that data. So for this to work, the chess system needs to say, hey, players, are you okay with me sharing your game with the computer? And then all these people need to try to gather that data, and then somebody will invent the algorithm. So fundamental, this is not doable without all the data that we want, and also the data that we need, because we could still use a lot of more data to do some interesting stuff.
Professor, what ethical considerations should researchers and developers consider when computer decides more things?
Yeah, so here there are two main dimensions. So the first one is going to be the one we were just talking about, which is in order for the computer to learn something, I need to be able to, or I need to be willing to provide it with the relevant data. So if I want the computer to learn about driving, we need drivers or people who are using those cars to say, hey, I'm okay with the computer knowing what happened. And some people may not be okay with it. Like some people may say, I don't want the computer to know where I am. or I don't want the computer to use me as an example of how to drive because I may not be a particularly good driver or I may not be a particularly respectful of the rules driver. And so now I don't want to be part of the system. In the chess thing, it will be maybe the same thing. Like I don't want other people to know how I play. Now, chess is particular because the games have been public before the computers were a thing. But I may be like, no, I don't want the computer to try my techniques. I don't want it to learn how to beat me. So I don't want to share the thing with them. So we have to be very careful that the information that we're using to train the algorithms, the people who originated them are okay with it. Like if I want to train an algorithm to create a pop song, now I have to get all these pop songs in the system. I should make sure that the people who created those songs are okay with me doing that. Sometimes we do that, sometimes we don't, but that is the fundamental initial issue, which is we are using a lot of information. We need to make sure that the source of that information is okay with us doing that. And then the other dimension has to do with the self-driving car is a good example here. So in the past, imagine I'm driving my car and I get into a situation where I have to decide between like hitting a tree or hitting a house. I don't wake up in the morning and think, hey, let's think about this. What will happen if next week I go in my car and I have to decide between the house and the tree? In general, we make that decision on the spot. So if that situation was ever to happen to me, I will make the decision pretty quickly. I'm probably wrong, but I will still do that on the fly. The computer doesn't work that way. So the computer cannot invent a solution on the fly. So that means that if I am programming the car, I need to be able to make that decision. And so now we have an issue, which is if I hit the car or the house, it has different implications. So who is responsible for this? Is the computer that did it responsible, or is the driver responsible? And in general, the computer is not gonna. It's not easy to make them responsible. So we have to, because there is no obvious answer. So here we need then the people using the algorithm to make some determinations as to what they are comfortable with seeing happening. And maybe we will have a car that is like the tree car, the one that hates the trees and hits the trees. And then we have the house one that hits the houses and so on. So there is a lot of decisions that we eventually may have to make that we delay until the problem is up to us, that now we have to make ahead of time so that the computer can know what our desires are. And so that is another weird ethical dilemma between me not thinking about that because I don't think it is likely, and me having to somehow make that determination or delegate that determination because the computer can drive without all those decisions being predetermined. So then, in my opinion, those two ideas, being able to get approval and consent from the people that are giving us the data, and figuring out who is responsible and what we want the computer to do in these very complicated scenarios, are the two main dilemmas that need to be resolved for this to continue nicely as a technology.
Yeah. Professor, looking ahead, what do you see, what do you foresee as the next big breakthrough in algorithm development?
That is in many fields. So the first thing that seems to be appearing is on the hardware side. So we've been programming using zeros and ones since the beginning, and that, even though we're so used to it that we don't notice, it does have some limitations. And so the whole area of quantum computer, which is becoming a buzzword now, that may help us revolutionize that a little bit. So having a different, or actually for the people who like this, revolutionize it a lot, which is it will change the paradigm of how we interact with the computer and what the computer can calculate. And that may bring a number of breakthroughs on potentially problems that we're already working on and algorithms that we already know how to do if we had a computer. So similar to what I was saying about the neural networks, we had that for a while, but we didn't have the computer. So now in the quantum area, we have a lot of fantastic ideas, but we still don't have the computer. So once that computer appears, we'll be able to evolve quite a bit. Then the algorithms that can learn by themselves will be another interesting idea. So even in the chess example that I was giving you, the algorithm is still not 100% learning by itself because I am giving it the whole set. So I'm giving them all the outcomes. That is not how I learned to play chess. Like I didn't study millions of and even hundreds of games. You have to be fairly advanced to do that. I learned chess by just much more simple interactions. So having an algorithm that can do that, so that doesn't need the universe of information to be able to do something, and they can figure it out directly, then that will be quite revolutionary. And it will be closer to, again, the human experience, where we don't sit there and watch a TV with all the information that we need to live our lives. If we go kind of step by step as we move, and a computer could potentially eventually do that, and that would be pretty revolutionary. In the chess example that I was giving, though, we are fairly close to that one because we are able to have the computer play chess against itself, so it can learn as they go, like playing with itself. But for other things where it's not interacting with itself, we will need to do this. And then this area called explainable AI. So right now, when we train an AI model, the calculations that are happening are so complicated that I don't know what's happening. So I know what the training is, and if you ask me to write a program, I can program the training, but I have no idea what the thought process is. To be fair, the thought process of the human is also equally obscure. Like right now, the procedure that I'm using to talk to you is not very explainable. Like you have to connect me to some stuff and figure out what my brain is trying to do, but this is flowing without exactly knowing what my brain is doing, or at least you knowing what it's doing. For the AI, it will be very interesting if we could eventually figure that out. So if we can get the AI algorithm, AI model, sorry, and we are able to figure out, okay, what is this trying to do, and what is that trying to do, and so on. Because that will give us a lot of insight of how the actual intelligent thing works. Where again, right now, we are just blindly throwing stuff at that and hoping it will work. And it does work. So that part is not the problem. The problem is that we don't really know exactly how it works, so it's very hard to tweak. The only things that we have to tweak the algorithm is to change the data set or some of the parameters, but it will be really nice to see what is actually happening. And then the last idea here will be what we call federated learning, which is the idea that we don't have to centralize the thing that we were saying. So right now, in order to learn better, you need more data. So the algorithm that has all the data is likely to do better than algorithms that do pieces. But it would be nicer for this to be the other way. So to be able to say, hey, in this particular area, we're going to give you the subset of the data and try to learn that, but also connect to the other one so you can share some ideas between your model and the other model. So we have some general principles, but the information. Similar to how we operate as humans, where if I live in a particular country, I don't have to have every context of everything, but there are some commonalities. So we can learn the common things together, the separate things separate. And so that is something that people are doing with like having their own language models and things like that. But it would be nice if the technology could evolve so that became the norm, as opposed to these totally centralized models where all the information is there, which is awesome, but eventually it's going to become expensive and too much information is needed. And so those would be my 4 top ideas or my wish list of the 4 things that I hope are happening in the future.
Yeah. Professor, last question. What advice do you have about algorithms for those interested in pursuing a career in computer science?
So there are 3 perspectives you can have in this if you're trying to study computer science. The easy one is that you actually don't pay attention. So if you are doing a career where you are using software, but you are not deeply developing something, so let's say you are developing a website, you don't really need to have deep knowledge of how all the algorithms of the server or even how the browser works intrinsically. So just fundamentals, make sure you don't write ridiculously inefficient code, but for the most part, you don't even have to call it an algorithm. You can just remember it's like, if I don't call this asynchronously, then it's going to be slow. If I call it asynchronous, it's going to be fast. So you can have a rudimentary level of understanding of how this works. The analogy I use here is like a driver. So when I drive my car, I don't have to know how it works. It's fine. I just know the mechanics, and I know if I press this happens, press that happens. And that is still a field, and you can be doing that for quite a while. So that'll be the first one. The second one is if you are the person actually writing something that requires fair knowledge of algorithms. That would be like when I worked at Microsoft, the people who are doing the cloud computing or the compilers or those things, they are writing something that is so fundamental that you have to have a very strong fundamental understanding of algorithms. That requires more studying. It's a lot of fun if you enjoy it, but it requires much, much more knowledge. And the idea there is, yes, you should learn how to measure all the things we are talking about, how to try to show that the algorithm ends, and how to measure how fast or slow it is. Actually measure it, not just like the impression, or this slow, this fast, but actually mathematically do the calculation. And that is where computer science tend to focus more, especially in the classes like data structure and algorithms, where we focus on teaching you how to read and measure algorithms. And then the deeper one would be if you want to be in the research area and now to invent new algorithms, so you are trying to evolve current algorithms. And that is also a lot of fun. It's a very small subset of the people that actually use computer science as a thing. Like again, when I was at Microsoft, we were not spending all our time inventing algorithms. We were implementing algorithms, tweaking them a little bit, but we were not writing brand new algorithms all the time. If you are like in academia, you can do that full time. If you are in industry, you can do that part time. Some people full time in some of these research businesses. And so that one does require you to do the whole thing. So you have to understand algorithms from the beginning, how they work, how they were created, look at the old ones so you can see the improvements, where the potential improvements are, what direction the improvement is coming from. So is it because of quantum computing? Like, is it because we have new hardware available? Is it because we have a new idea available? Is it because we have new data available, and so on? And that would be the deeper fit. But all of these have a match. So some people, again, prefer to do the high-level things. Some people prefer the middle-level things, and some people enjoy the lower-level things. So when people think of computer science, historically, they tend to associate it with the lower-level thing, like I'm going to have to write 0, 1 things to the computer. But that is not necessarily true anymore. And you can do a lot of fun computer science things without having to go that deep. But so I always tell people, just give it a try, and then the one that you enjoy is probably the one that you're gonna have a better time with. And I've met students who enjoy the 0, 1 things, and when we do exercises that have to do with very low level operation of the computer, they're very happy. And there are people who enjoy more like, okay, how do I develop my website, and which color I want to use here or there, and which algorithm I'm going to use to do this particular thing. All of these are fair things that people can do in life. So just I always tell them, just give it a try, and hopefully one of those will be fun.
Professor Marcelo, thank you for joining us today on this insightful episode. We are truly grateful for the opportunity to explore the evolution of algorithms and their profound impact on technology and decision making. We hope our listeners have gained a deeper understanding of the intricate world of algorithms and the exciting development on the horizon. Thank you once again, Professor Marcelo, for sharing your expertise with us. We look forward to seeing how your work continues to shape the landscape of technology. Thank you, Professor Marcelo.
My pleasure. Great. Thanks for having me, and I look forward to working with you some more in the future.
Thank you.